Hello, my name is Aaron Balke, and in today's video I will be breaking down my K-means clustering analysis for my Master's in Data Analytics. This presentation was originally made for my assessment, and so there may be some assessment-specific stuff in here. Just be aware of that as you are watching it. And this assessment originally used a theoretical hospital data set of patient demographic information, health information, in order to do the analysis. With that all in mind, I hope you enjoy the presentation. Hello, my name is Aaron Balke, and in today's video I'm going to be breaking down my D212 Task 1 Clustering Techniques Performance Assessment. For this performance assessment, I'm going to be using K-means clustering, and I want to try to figure out if we can group patients based on features heavily correlated with the length of their initial hospital visit. And so the hope is to use K-means clustering on the heavily correlated features of the initial days feature in order to see if we can gain any sort of insights into patient characteristics related to the length of their stay, so that we can allocate human and medical resources effectively for those patients. Because if we're able to see how long their stay is going to be, we can figure out, something like meals, how many meals we're going to need for those patients. And we're going to be evaluating the model based on an average silhouette score. So that is the goal of the analysis. We're using K-means clustering. K-means clustering uses vector quantization in order to group data into X or K number of clusters. And each cluster has a center point called a centroid. And from that center point of the cluster, we look at all the data points and we try to figure out which centroid they're closest to, and then we put that in that cluster. And the assumption, the reason we do that is because we assume that data points that are close to each other based on features have similarities. And so if they're all near each other, they must all have similar characteristics. And so our hope is to get the most correlated features of initial days and then start to try to make little clusters inside those features. The assumption of K-means clustering, it's a distance-based algorithm, and so the big thing we have to keep track of is magnitudes of our variables. We want to standardize and scale all of our variables to be the same size. This is similar to KNN classification. Any distance-based algorithm, we want to make sure that there aren't one variable that has a massive scale and massive magnitude, and then one that has a very small one. We want to make sure they're all on the same scale. That way there are no skews in our outcomes. And this also means we can't use categorical variables or binary variables. We can only use continuous variables. For today's analysis, we are going to be using Python version 3.10.9. We're using Python because I'm most familiar with it. It's the most straightforward language I've ever dealt with. It has strong data analysis support, and it has a ton of great libraries and modules that we can enhance our capabilities with. We can automate a lot of stuff, and we'll go over those a little bit later. We also are using Jupyter Notebook version 6.5.2. We're running Python in a Jupyter Notebook environment because Jupyter Notebook provides the checkpoint functionality, and the checkpoint functionality allows us to save the state of our models and go back to them at a later time. That way we don't have to keep running things we've already ran before. We can save the outcomes and the results of our models and just go directly to those instead of having to reload the state of them every time. We are using pandas because of data frames. I don't think you can do data analysis without data frames. At this point, I am sold on data frames. Data frames are amazing. We're also using NumPy. NumPy allows us to do some more intense computing, some more intense stuff easier. It abstracts out a lot of calculations like averages, absolute values, dealing with NaN values, all of that good stuff. We're also using Seaborn and Matplotlib. Both of those are being used to help with visualizations when we're evaluating the model and when we're pre-processing to make sure we're on the right track. And then the other big one we have is sklearn. Sklearn is providing a lot of this analysis's objects and methods. So for example, the standard scaler for scaling the data comes from sklearn. The silhouette score metric is coming from sklearn. That allows us to choose the optimal clusters. We also have the Kmeans model object, which is the actual analysis method and object that we're going to use to do the clustering. So sklearn is going to be very important today. When it comes to the preparation of the data, the main goal is going to be, as we mentioned before with the assumptions, we have to standardize the scaling of the data. We have to make sure it's all on the same scale. That way we don't have any skews based on one specific variable or another. And then variable-wise, we can only use continuous variables. We can't use any sort of categorical variables, any sort of binary variables, and so we are stuck to only having these 7 here: the latitude, longitude, income, vitamin D levels, initial days, total charges, and additional charges. So we are stuck to just those 7 variables. The nice part about not having all those categorical and Boolean values is we do have way less preparation steps. So we don't have to worry about dummy feature creation. We don't have to worry about conversions. All what we have to do is drop all the unused columns and then scale the data. And so first thing I'll do is restart and run all the cells to show you it works. Hello. There we go. And while that is running, we can go over the imports here. The standard imports, we got pandas, numpy, matplotlib, seaborn, and then we have those sklearn imports I mentioned previously. So Kmeans is the actual model object itself. Silhouette score allows us to evaluate the effectiveness of our model. And then standard scaler scales our data to all be the same scale. Then we got the data being imported, the medical data here. We then drop all of the unused features, and it was simpler just to mark all the ones we're keeping than it would have been to mark all the ones we're not. So I just marked latitude, longitude, income, vitamin D levels, initial days, total charges, and additional charges. Then we got the scaler here. Just using the standard scaler, we fit the data frame and transform the data frame to the scaler, get back out the scaled data. It is returned as a NumPy array, and so we need to convert that back into a pandas data frame, which is what we do here. And then to verify the scaling, we check on the standard deviation of the scaled data, which should be 1 or very, very close to 1, which it is. So it's 1.00005, so it's close. So we've scaled the data there. We then export the data here, so that exports it as a CSV file. And then we move on to the actual analysis. And the first step of our analysis will be getting the optimal clusters. Well, I guess even before that, the first step will be choosing the features we want to do the clustering analysis on. And as we mentioned, we want to try to get the features most related to initial days. And so what we're going to do is we're going to check for correlation using Pearson coefficients and feature correlation. We're going to use that to get the 2 most correlated variables, and then we run the clustering on those 2. We'll have to evaluate the variables to try and figure out what the best amount of clusters would be. And so I guess I'll show the correlating part first here. So we're just getting from the scaled data frame the correlation values, and then I filter it to just be the initial days correlation values. We get that, and then we plot that on a seaborne heat map, which is what this is here. So as we can see, the two most correlated variables are total charges and additional charges. Those are the two with the highest correlation to initial days. And so those will be the two variables we run the clustering analysis on. We then do make the clustering data frame, which is just the total charges and additional charges from the scale data frame. So that's the new data frame here. And then it will be a matter of choosing the optimal clusters. And I went with two methods, one of which was the inertia elbow method, and then the other one was using the silhouette scores to choose the optimal one. And I used both because the elbow method can be a little vague sometimes if it's a shallow enough curve, so it's a bit hard to tell where the elbow is, which was what happened in our case. And so I decided to use both of them just to be on the safe side and get a better conclusion for the optimal clusters. And so the inertia elbow method, that uses the inertia, which is the within cluster sum of squares value, and so that's the distance between each data point and its centroid of the cluster, squaring that distance, summing all the squares of that cluster's data points, and then using that as a score. And so let's show that graph here. It does have a high score at the beginning, so the less clusters, the more higher the higher the score will be no matter what. But we want to try to find the elbow because we want to also balance the number of clusters with the score itself. And so for our elbow here, I was debating between it being either a 3, 4, and so I wasn't sure if it was 3 or 4 from this graph, and that's why I needed the silhouette score method to get the rest of that. The actual code itself, we have a range here, so that's the number of clusters. We do have to start at a range of 2 because a silhouette score is based on the previous value, and so we can't run it based on one cluster only. We need to start on 2. Also, having one cluster with cluster analysis seems kind of like a waste of time. So we're going to start at a range of 2. And I went up to 7. Previously, I went up between 10 and 20. I was messing around, and it did not, it flattened out the further on you got, the elbow plot did. So just did it at 7 for this presentation. Then for each cluster amount in that cluster range, so from 2 to 7, we run a Kmeans model with that many clusters. So first one would be 2, second one would be 3 clusters, 4 clusters, etc. And we fit the cluster data to that K-means object and then get the inertia values from that K-means object. And we append that to a list I have outside of the for loop here. We also do the silhouette score. The silhouette score is a metric to show how distinct the different clusters are, how easy it is in order to distinguish those different clusters from each other. So if they're overlapping a lot, if they're I don't know how to visualize it, but if the distributions of those clusters are overlapping a ton, you're going to have a very low silhouette score, and it ranges from -1 to 1. So anything over 0 would mean that it is able to distinguish the clusters. Anything under 0 is it couldn't distinguish the clusters. So we get both the inertia value in order to do the elbow plot, and we also get the silhouette score in order to do the silhouette score plot, and we plot both of those. And these are the two, I can't fit both of them on there at once. These are the two plots here. The elbow method, as we mentioned, we want to see where that elbow is, which is around 3 or 4. I wasn't entirely sure at this point. And then the silhouette score, we just want the highest value for the silhouette coefficients, and in our case that is 4. Barely beats out 3, but 4 is more optimal than 3 clusters. So when we go on to do the actual analysis, we're going to use 4 clusters as our K value. And so for the actual analysis, we create another K-means object, and this time we do input 4 clusters. We then fit the cluster data to it, and then run a prediction on the cluster data frame, and we get back our Y prediction. I just immediately took that Y prediction and marked it on the clusters data frame, or the data frame as a clusters feature. And so at this point, I decided I didn't need to worry about the scaled data anymore since we fit the model and we got a prediction. And so I just put the clusters back on the unscaled data. That way we can compare the clusters to the actual values of the different features. And so here's the head of that data frame. So we're able to see for the first record all the latitude, longitude, income, vitamin D levels, initial days, total charges, additional charges, and now the cluster it fits into as well. So we can see that fits into cluster 2. I then decided to take the data frame and get the data frame split up by which cluster each record fit into, and this will help us when we go to plot it down here. And this is the plot itself. I have 4 different scatter plots, 1 for each cluster, and as we can see, each cluster is very effectively distinguished from each other. We're able to see a quadrant for each cluster, so it is able to visually we can see it's able to distinguish the different clusters and make groups based on the clusters. So this was great to see that the clustering actually works. So so we got the clusters, the K-mean clusters, we got 4 of them for total charges and additional charges. So we can see there seems to be a cut in the total charges at around $5,200, and then a cut along additional charges about $16,000 or $17,000. So that's kind of how we split these quadrants up. So as I mentioned, we can visually see the 4 distinct clusters. The average silhouette score will, though, that will give us a evaluation metric in order to actually know for sure that it is split and evaluated correctly to confirm it. And so, as I mentioned previously, the silhouette score ranges from -1 to 1. A score above 0 shows that the model can distinguish the different clusters easily, and a value under 0 means it cannot. So we want a positive value over 0. And when we run the silhouette score on the clusters and get the average silhouette score, we can see we're sitting at 0.55, which means we do have a model that can distinguish the different clusters effectively. So that is great news to hear, and we're able to, the model is effective. Onto the results and implications. So results, our average silhouette score is great, which means the cluster analysis is working. We are able to see that there are quadrants. There are 4 distinct groups. We have the high total charges, low additional charges group. We have the high total charges, high additional charges group, low total charges, low additional charges group, and the low total charge, high additional charges group. So the actual analysis works perfectly fine, but onto the implications of this analysis, this is where it begins to fall apart. What we have to do next, and the thing that would be most useful for our research question, is to try and see when we aggregate the values of these clusters, how do those features, how are those features painted, and are we able to gain any insights from aggregating those clusters? You know, do all of the values in group or cluster 1, do all of those have a certain initial days value? Do all of them in cluster 2 have a certain initial days value? And so that is the purpose of this next portion. And when we take a look at this, we can see that initial days is the same or roughly the same for clusters 0 and 2, and roughly the same for 1 and 3. What this means is, by taking a look at the additional charges and total charges, it means that the initial days variable is heavily, it's being thrashed around by our total charges feature. Because as you can see, the total charges feature has a similar value or similar magnitude at initial days of 9, and it has a similar magnitude at initial days of 5960, which is not the case with additional charges, which seems to be the same for 0 and 1 and different for 2 and 3. And so this kind of goes back to the initial correlation, Pearson correlation coefficients and analysis we did prior to actually choose the variables, and that was that the total charges variable had a strong correlation of 0.99, while the additional charges only had a correlation of 0.004. And so this total charges variable explains most of the initial days variable, or vice versa. The initial days explains most of the total charges is probably what it is most likely how it goes. But what that means is this additional charges is only affecting around 2 or 3% of the initial days value, while the total charges is completely controlling most of that value and how the clusters are being made. The problem with that is that we're unable to actually gain any insights on the initial days variable from our cluster analysis on additional charges and total charge. So unfortunately, we're not able to answer our research question of what sort of characteristics affect initial days, because the total charge was pulling it around so much is what happened. And part of the problem with the main limitation of this analysis and of K-means in general is that the K-means model requires continuous variables. And so we had 50 plus features, but only 7 were continuous, which means all of a sudden our data was extremely limited. We cut down to less than 20% the data we had beforehand, and so we're having to only use 7 features, and of those 7 continuous features, the latitude, longitude, and income, those are very general data. Latitude and longitude is I don't think there were any variables that had any correlation with those two. I'd have to double check again, but very general. The income was a very general piece of data, demographic data. And then the total charges and additional charges were financial features that get added after the patient's visit. And so we're not going to be gaining a lot of health-related characteristic insights from those variables. The only health-related feature we had in this analysis was the vitamin D levels, and I believe that if we had a continuous either like high blood pressure value, so maybe a pulse, systolic or diastolic value, a overweight value, maybe like a BMI, or other individual blood tests, there's a lot of different like lipid values that are continuous variables. If we had any of these other health-related characteristics as continuous variables, I believe we could have made more insightful analysis. And so going from that limitation to my recommendation is not to make any conclusions at this time using this analysis, but I would request the ability to get access to continuous variables for a lot of these variables we have Boolean values for, such as the high blood pressure, such as the overweight, and other variables as well. Just if we had continuous variables, I believe we would be able to make more effective analysis of the data set. And so it would be, either the hospital needs to start recording these variables as continuous variables that we then convert to binary if we have to, to a no high blood pressure feature, or we need to begin sharing the data in a continuous variable form instead of just giving the Boolean variable version or the categorical variable version. I believe that will be important for better overall analysis. And I'm so staunchly on this because this is the second or third time that this has occurred where having only Boolean or categorical variables for stuff is causing problems in my analysis. So I would heavily recommend we get continuous variables or more discrete variables instead of just categorical and Boolean features. So that is my recommendation for D212 Task 1 and my cluster analysis. I hope you enjoyed and hope you have a good one. Thank you.